So in the last lecture, we had discussion on continuous counter current dryer, and the way we tried to model it, we divided this dryer into 3 regions. Okay, and we said that the division of such regions is quite arbitrary. Arbitrary in the sense that in some cases it's possible that you have a very small length for heating of the solid surface, so that can be made negligible. In some dryer it's possible that after the moisture content has been reduced to a certain level, then we don't have the further requirement of heating of the solid or adjustment of the solid temperature, because maybe there is a risk the solid may decompose, right? So in that case we said that in general we have, from the modeling point of view, 3 regions. In one region, when the solid enters, it's a unbound moisture region, so there we have constant drying rate. Then moisture content decreases to critical XC, all right. Then beyond that we had this bound moisture region, so there the moisture content decreases from XC to whatever is the desirable concentrations. Now there also we made some simplifications. We assume that from mathematical point of view, we assume that there is a linear decrease all the way till whatever is the requirement for our in our example, even if we have hit or we have gone past this capillary effects region, all right. Then we can have some region where there is a post heating. So these are the 3 regions we had a specific focus in the last lecture. Then we derived certain expressions, how long will it take, or what is this theta, a residence time we have to give to the solid in contact with this hot air to bring a concentration from decrease from one level to another level, all right. So in today's lecture we take an example on this continuous counter current dryer, all right. So this is an example on continuous counter current dryer, all right. So the problem statement reads like this. Let's draw the schematic first, and let's divide into 3 regions. So we have region 1, 2, 3. Let's mark it 1 on this interface here, 2, 3, 4. So now it reads that solid say enters from one end. It's a wet solid, so it has a moisture content 25% or 0.25. Now when we say 0.25, this is kg of moisture per kg of solid wet basis. So for our case we will write it as x prime for the wet basis, so that we can calculate x or x1 for this entrance here as 0.25 equal to 0.75 equal to 0.333. So the wet solid enters with the moisture content dry basis at 0.333, right. The flow rate of this solid is given as 100 kg per hour. Now the temperature is not given here, all right. So we'll come back to this. T1, if you call it, Ts1 is not given. To dry this solid, we have hot air entering from the other end. So the temperature here is Tg4, 4G for the gas and 4 for the excitant. Temperature here is say 100 degrees centigrade, all right. And this gas flow rate or air flow rate Gs is 12,000 kg per hour, and the humidity or the moisture content in the air, so that's Y4, is 0.025 kg per kg dry basis. So this flow rate is also on the dry basis, okay. And it says that this solid has to be dried to the temperature Ts4 60 degrees centigrade, and the moisture content x4 prime wet basis is 1%. So quickly we can calculate here x4 as 0.0101. All right. So the solid has to be dried from 0.333 to 0.0101. Flow rate of the solid is given, flow rate of air is given, moisture content of Y4 is given here, and the temperature here is given. All right. So this region, so the gas which comes out has temperature Tg1, which is not known to us. It has humidity Y1, which is also not known to us. And interfacial, all this for the gas or for the solid, we have to calculate whatever be the temperature or this moisture content in the air phase or in the solid phase. All right. So now when we said we have divided into 3 regions, the first region is unbound, second is bound, the third is heating or post drying. All right. So now the problem also read like this, which we should note down: temperature of the wet solid entering the dryer, all right, is approximately equal to adiabatic saturation temperature of the air leaving the dryer. So we should pay attention here that the solid temperature of this wet is same as, not Tg1, same as the adiabatic saturation temperature of air leaving this dryer. That's one. We'll come back to this and see what does it mean. Number 2, we also assume that solid remains at this adiabatic saturation temperature Ts throughout in this region 1 and 2. All right. So before anything else, let's discuss what it does mean. If you recall in our previous discussion, we say that when we have a solid bring in contact with some hot air which has temperature Tz and humidity Y, the film on this, so if the solid is moist covered with some thin film, we are talking of this unbound region, the moisture will evaporate, water will evaporate, and the solid temperature will decrease till it reaches an equilibrium with Ts. All right. So under steady state, we have the surface temperature as adiabatic saturation temperature, or this could be wet bulb temperature. We talked about this. If you neglect the radiation effect or conduction effect, then the surface temperature will be wet bulb temperature. Otherwise, it reaches the adiabatic saturation temperature corresponding to this air quality. So that's very important that we understand here. And then once it reaches Ts, so we can assume that throughout the solid has the surface temperature is Ts. So that's what it says. Solid remains at Ts, not only in this region 1, in the region 2 also. All right. Now this is first assumptions that solid remains at Ts in the region 1 where we have this unbound moisture is quite acceptable. However, when we have the region 2 where now the drying rate has decreased and maybe it goes past this, after going past this Xc, it reaches the region where we have the capillary effects. So now we are talking of moisture which is being driven from inside. There it's a bit rigorous assumption to assume that the solid surface temperature will remain at Ts. So nonetheless, in this, that's an approximation that throughout in this drying region, so region 1 and 2, it's a region where we have this drying, whether bound moisture or unbound moisture, solid remains at this Ts temperature. So and this Ts is same as adiabatic saturation temperature of this air which leaves. All right. So that's a very rigorous 2 assumptions we have made here for our calculations, but you will notice that the first one for the region 1, it's a quite a very good assumptions. For the region 2, bound moistures, maybe if it reaches this capillary regions, then it's possible that this region there will maybe some error there. All right. Nonetheless, now after it has reached this first unbound region, the moisture content is now Xc, and it says problem Xc is given to us, its value is given as 0.087. All right. So again, notice here, if you recall, we said that in this drying, this critical moisture content or equilibrium moisture content, they have to come from equilibrium, this characteristics curve. In other words, one has to do this experiment. You have to take the same solids and simulate in the lab under more or less with the same Reynolds number of the gas fluids, the same temperature or the solid surfaces to which it's exposed in the laboratory. So one has to establish this drying curve, which we have been using it quite rigorously in the first lecture on this topic. All right. So in this problem, Xc is given as 0.087 kg of moisture per kg of dry solid, and it says that Xe equilibrium is approximately 0. Now this is also a very good assumption. Maybe the moisture content in the solid under equilibrium is very, very small. Actually it cannot be 0, but nonetheless for our case we assume it is 0. Okay. Now all physical properties or some thermodynamic properties are given to us, but before that let's mark it here. Let's try to understand that now we have Xc is known to us 0.087. So moisture content will decrease from here to here, 1 to 2. So X1 0.25. Now X2 is same as Xc, 0.087. Now it will further decrease at X3, but we do not know what is X3. But notice that this is a heating region. That means solid temperature only changes, gas temperature only changes, moisture content will remain the same. So we know X4, that means X3 equal to X4 equal to 0.0101. So X1 is known to us, X2 is known to us, X3 is known to us, X4 is known. So we know all the moisture content. Surface temperature, solid Ts is not known here, here or here. All right, but we know the exit temperature, which is 60 degrees centigrade. That's the quality of our product. Let's look at the gas phase. Air humidity is known and air temperature is known. So nothing happens here in the sense that there is no moisture evaporations, all right, from the solid. It's just a heating. That means Y3, humidity of the air at this interface 3 and 4 will be same as 0.034. So we know Y3. Y2 is not known to us, nor Y1 is known to us. So the question here is find out total theta. Theta 1 region 1, theta 2 region 2, theta 3 region 3. How much contact time, how much resistance time we have to give to bring this solid content from here to here with the specification whatever is given to us here. All right. So the problem like this, if you recall from our the previous lectures discussion, when we had this analytical solutions, analytical expressions, one has to identify what are the humidities and the solid moisture content. So before that, let's draw another schematics for our calculation purpose. That now we have 3 regions. Solid temperature, it increases like this, you will expect. So we have Ts1 enters, Ts2, Ts3, then it further increases to this Ts4. Moisture content X1, X2, X3, X4. It's good that we draw some type of schematics here. Air temperature will decrease, so you have Tg4 decreases, Tg3, all right, Tg3 here decreases to Tg2 and then decreases to Tg1, which is the exit temperature. Humidity, corresponding humidity is Y1, Y2, Y3, Y4. All right. So before doing any calculations, maybe we should draw this, all right, and see what is given to us, what is not given to us. X1 is given to us. Let's put a tick here. X2 is given to us. All right. X3 is given to us. X2 is nothing but Xc, critical moisture content, and X4 was given to us, but we said that X3 equal to X4 because this is region 4. So all the 4 moisture contents are known to us. All right. Ts4 is the degree exit temperature of the solid, which is also given to us 60 degrees centigrade. So we put a tick here. Tg4 is given to us 100 degrees centigrades. Y4 is given to us. All right. Y3 is same as Y4 because there is no moisture, there is no evaporation here, there is no drying here in this region 3 and 4. So Y3 is also known to us. All right. Now, what are things not given to us? Tg1, Y1, Tg2, Y2. All right. So these are, you have to calculate Tg3 and your Y3. Y3 is given to us. All right. So how do we what is the approach? So first thing is that before we make any calculations for theta, we should try to make overall enthalpy balance, overall moisture content balance, or over the certain segments, so that we try to evaluate as much as quantity given to us here. All right. So in this case, again, now when we want to calculate the enthalpy, so let's say how do we calculate solid enthalpy at any locations between 1 and 4? Hs will be equal to, say, CPS. So this will be specific heat of the solid. Say if we choose 1 kg of, or 1 unit weight of the solid, this will contain X amount of moisture. So we'll have CPW. So 1 kg contains X kg. That's the moisture content. Ts, solid temperature at any location here, minus some T reference. Generally, you can choose T reference as 0. There's no harm in this, as long as we are consistent here. Okay. Then comes Hg, air content. All right. What is the specific enthalpy kilojoule per kg of air here? So similar to the CPS, now you have Cp air plus, instead of X you have Y. So that's the humidity, CPW, but this is now moisture. All right. Specific heat of vapor or in the solid, which is the liquid, will be different from what we have in this moisture. We call it moisture in the vapor phase. So that's one place, although both are H2O, water. One is a condensed phase, liquid, and one is water vapor here. Into Tz minus the reference temperature, which is 0, plus there should be one more quantity here, that's your Y into lambda. So from this reference temperature, we have raised the temperature to this Tg, and then we have evaporated this moisture here, or water here, by this latent heat of vaporizations. So these are the two general expressions, one for solid, one for air. You should notice that that means if we know Ts and X, we can calculate Hs, or given Hs, if we know X, we can calculate Ts. Similarly for air, if we know Tg, if we know Y, we can calculate Hg, or if we know Hg, enthalpy at any locations, we know the humidity, we can calculate this air temperature. So with this overview, then we should make our general calculations here, what is given, what is not given to us. All right. So if you recall, in the earlier class also, we had started with region 3. All right. Then we had region 1, and then we went to region 2 to calculate all this theta here. Okay. Let's make note of certain other properties which are given to us. So in this, what is data? Some data, thermodynamical, thermophysical data are given to us. So Ky, mass transfer coefficients, 150 kg meters per meter square per hour. A prime, we said that it's a specific effective area of drying. So for the solid, this is 0.65 meter square per kg dry basis. CPS, so a specific heat of this solid alone, no water. This is given as 0.96 kilojoule per kg per Kelvin. Okay. So these are the physical thermodynamic or physical properties given to here. Now we can calculate all these quantities which we are supposed to calculate here: Tg1, Tg2, Y1, Y2, Tg3, Y3 is known to us because Y4, Ts1, X1, X2, X3, T1 is also not given to us, Ts2, Ts3. So these are the circles which you have to calculate. The one we have ticked here, X1, X2, X3, Y3, Y4, Tz4, Ts4, they are known, or we have at least make this small calculation that X3 equal to X4 and Y3 equal to Y4. All right. First thing we would like to do is, that's a good practice, we should make overall moisture balance. Let's see what we can calculate here. All right, in the gas phase as well as in the solid phase. So let's make it overall moisture balance. So overall moisture balance would be GS Y1 minus Y4. So inlet minus outlet equal to SS X1 minus X4. So it's a continuous counter current, 1, 4. Air goes like this, solid goes like this. So whatever is lost in the solid is gained by this air here. Now look at this, we know GS, so let's put the number 12,100 y1 is not known to us. All right, so this is, so we have 1 here and 4 here at the end. So it's overall moisture balance. So y1 is not given to us. So y1 minus y4, which is 0.025. So that's here. SS is 100. X1 is here, moisture content. We calculated 0.333 minus x4. We have to bring down to this level of 0.0101. If we do this, y1 equal to 0.0452 kg per kg, all dry basis. So we have calculated y1 now. All right, so you can go back to the previous slide and you should put a tick here. So y1 we have calculated. That's the first thing we have calculated from overall balance. All right, so this is your y1. After that, what we should do here, again you should inspect that what are the things we can calculate by another balance over the regions. So let's see if we can make another material balance between 2 and 3. So this is 1, this is 2, this is 3. All right, let's note down here GS y2 minus y3 equal to SS x2 minus x3. Okay, so notice this, that y3 is known, so let's make it 4 here. Y3 is known to us because y4 is same as y3, no moisture evaporation, so y3 is given to us. GS SS is known to us. X2 is known to us, that x2 equal to xc, and x3 equal to x4, so this is also known to us. So from this we can get y2, 0.0298 kg per kg here. All right, so go back to this now. Same schematics which we drew here. We had 4 regions, 1, 2, 3, and 4. All right, all x1, x2, x3, x4, y4, y3, y2, and y1. Now we have calculated all 4 of these quantities. All right, that means now if we know the temperature at any location, if we know the temperature of solid or if we know the temperature of gas, then we can calculate enthalpy HS, or we can calculate enthalpy in the air phase Hg. Or if we know HS and Hg, and since we know all the 4 here, the humidity and the moisture contained at the 4 locations, we can calculate the temperature of solid or temperature of this gas. So this is what we are supposed to do here before make any other calculations. You draw the nice schematics and put as many quantities which are given to us. Then more important here is that definition for your enthalpy for the solid and enthalpy for this air. If we know the moisture contents either in the solid phase or the humidity moisture content in the air phase, then knowing the temperature we can calculate the enthalpy. Or if we know the enthalpy and we know the moisture content in any of the 2 phases, we can calculate the temperature. So then we can go back and directly substitute in the expressions for your theta, residence time or the time required for heating or decreasing this moisture content from one level to another level. So here all we have done, we just made overall material balance, we made certain approximation there, x3 equal to x4, no heating, etc. So there we calculated y1 humidity which is not given to us, and then from y1 we calculated y2. So we made overall moisture balance, and then between region 2 and 3 we made another moisture balance. All right, now let's make some other calculations here. Now let's start with the region over 3. Okay, so that's what we did when we developed our expressions for theta contact. So now we are talking of the last 3 and 4 region. Again, recall our discussion. Here we have the solid living like this and air coming like this. For this, when we wrote down this balance for energy balance here or the heat load, we said that we have to make certain approximation, certain iteration, so we have to assume certain surface temperature. So if you write down this energy balance again, GS, let's say CH, TG4 minus TG3. So now between this region 3, whatever is lost by the solid energy is gained by this air. So we have SS, HS4 minus HS3. All right. So Tg4, it's right here. So that's given to us. That's known to us. Okay. But no other quantities. So of course, the flow rates are known to us. SS, GS, SS4 here. Okay. We have to see that how we can calculate other quantities like HS4 and HS3. So we follow the same approach what we had before. How we can get HS4? So let's write down the expression for HS4. HS4 would be CPS, same expression, which is 0.96 plus moisture content 0.0101 multiplied by specific heat of water, so 4.187 into this temperature, so 60 minus 0 degree. That's the reference temperature. So now this is enthalpy for this at the number 4 here. Here we know the temperature 60 and we know this moisture content 0.0101. So which means we can get HS4. So we can calculate this quantity HS4 here. Okay. Now let's see what is the CH. So from here CH, of course we require to know what is the CH here. So CH would be, again this is specific heat of your this gas which enters here. So this CH we can use as Cp of a dry air. All right, plus we have CPW of moisture content of moisture 1.88, and then you have into Y4, and but Y4 is same as Y3 here, okay, because there is no heating here. So Y4, Y3 they are known. We can write CH as 1.005 plus 1.88 into 0.025. So that's your 0.025 humidity is given to us kg per kg. So if you calculate this, you have the number 1.052 kilojoule per kg of dry air. Okay. So after this, now one has to make, if you recall our discussions, we do not know other temperatures here. Okay, we do not know surface temperature here, and we said that the solid remains at this temperature, which is adiabatic saturation temperature of the air which leaves at the exit 1. So we have to assume this number. This is the approach we had earlier also. One has to assume the surface temperature. Let's assume this Ts is 40 degrees centigrade. So what is this Ts? Ts is nothing but T1. Solid enters at adiabatic saturation temperature of leaving air, and it remains at that temperature. So T1 is the solid temperature, which is same as Ts and which is same as adiabatic saturation temperature of leaving air, and this will remain in the region 1 and the region 2. So now we assume this and we substitute. So if we substitute, let's say GS 12,000, CH we calculated 1.052 just now, Tg4 is 100 degrees centigrade temperature here of air 100, minus Tg3 is not known to us, Tg3. SS solid flow rate we know 750 into now HS4 minus HS3, so which is nothing but solid specific heat, which is 0.96. all right, HS3 here into 60 minus 40. all right, this is what we are doing, 60 minus 40. So 60 for the solid temperature, that's the leaving temperature of 60, and we have assumed 40 degrees centigrade, and the solid remains at this temperature throughout. From the region right here, this temperature is constant at Ts, so minus 40. So from this one can get Tg3. If you calculate, Tg3 is 99 degrees centigrade. So that's the way we did it earlier. We are making a balance over this region 3 after we have made overall balance moisture content. all right, so now we get Tg3. So this is the way we have to move to the next region and see how we can calculate here. Okay, so now if we know Tg3, which is we calculated as 99 degrees centigrade, Y3 equal to Y4, 3 and 4 is in 0.025. Ts we have calculated, or we have assumed as 40 degrees centigrade. Now if you recall, we have to check whether this Ts 40 degrees centigrade what we have assumed is not correct or not. So for that also, if you recall our previous discussions, if we have a psychrometric chart, and we know the quality of air which is entering here. So we know this humidity, we know this air temperature Tg4, which was 100 degrees centigrade, we know Y4. There will be adiabatic saturation line which will hit this Y versus T degree centigrade, and this would be your Ts. So from this Ts, if you know this temperature, if you go back and see, you will get back this 40 degrees centigrade. So that means our assumptions given to us was correct here. Okay, and once you know this Ts, we have this Ys equal to 0.05. So we can read from this Ys. Okay, now let's look at rate of heat transfer. So still we are working on this region 3, rate of heat transfer. So this region 3 heat load Q3 is Gs Ch Tg4 minus Tg3, which is 12,000 into 1.052 into 100 minus 99. So that's the temperature drops from 100 degrees centigrade air to the region here at 99 degrees centigrade. So if you calculate this, we have 12,620 kilojoule per hour. Hc, heat transfer coefficients, is nothing but Ky into Ch. We have to calculate all this quantity because we are going to use the expressions for the heating, all right, in this region. So in that we require Hc, and if you recall, the definition for Ch, humid heat of this air, is ratios of heat transfer coefficient and mass transfer coefficient. In the example, mass transfer coefficient was given to us and humidity we had calculated from this 150 into 1.052 is 158 kilojoule per meter square per hour per Kelvin. So we know this air temperature decreases from 100 to 99, and the solid temperature has increased from 40, which was the adiabatic saturation temperature, to 60 degrees centigrade. So we can find out del T1, del T2, LMTD. I leave this an exercise, very simple. Delta Tm will be calculated as 49 degrees centigrade. You go back to the expression for time of heating for this region. If we know heat transfer coefficient, we know the flow rate Ss, we know this driving force for heat transfer. Time of heating theta 3, if you call it, is very analogous to mass transfer Q3 divided by effective weight, amount of the solid in this region, into Hc del Tm. Q3 is we have calculated just now. Ss is given to us, A dash is given to us, Hc we know, delta Tm we have calculated. Here if you do this theta, we will get approximately 0.033 hour. Sorry, so if you this theta 3, this will be 0.033 hour, or this will be equal to approximately 2 minutes. We should spend some time here how we are getting these expressions. All right, so if you go back and recall mass transfer, we talked over this region of any small region del z. So we are giving some theta residence time. So this Gs spends say del theta. So we have so much of kg of solid over this time del theta. So it's like a batch. Of course, we have the continuous process, solid continuously flows like this, but we are saying that over del T, certain batch of solid is getting heated. Okay, so what we wrote in case of mass transfer coefficient in C as Ky Ys minus y, and we equated this to Ls del x del theta with Ls a prime. So what we have is a batch. We are trying to make an analogy with the batch of operation with the continuous. So you should go back to the previous lecture and see how we have obtained the expressions for heat transfer coefficient. So similarly, based on this, what we did, we integrated, or we wrote like theta, how long will it take, as Gs Ky Ss a prime ln Ys minus y2 over Ys minus y1. So this was derived for mass transfer aspect here. making the same analogy that certain batch of the solid is getting heated in this region, or all we have this time of heating theta 3 as Q3. So how much is the heating load divided by SS A prime. So that's the analogy. SS A prime, KY, we have HC, GS, we have this Q3, and we have this del T LM, logarithmic driving force here, or temperature. So we have the same analogy what we did here in the case of heat transfer to mass transfer to obtain theta 3 as 2 minutes, very approximately 2 minutes of this. Okay. So now what we should do here, again, since we know this theta 3, now we should move to the region 2 or region 1 to see what calculation we can.